Balancing equations, a means to account for the law of conservation of mass. A chemical equation is a process by which we can convey information about a reaction. They're used frequently when we're talking about reactions in chemistry rather than simply about particular substances. And they consist of several parts. They have reactants, which are the materials which begin the reaction, which is the state the matter starts in. Products, which is the state the matter finishes in. And the conditions, which are any special processes or means by which we conduct the reaction to make it work, other than simply the reactants and then the products that are formed from the reactants. In order to construct a chemical equation, we have to have some specific information. We need to know the chemical formulas of every species involved in the reaction, both reactants and products. We need to know the states of matter for every chemical in the reaction. There are 4 basic states of matter that we talk about, which sounds odd because there are only 3 states of matter. But we represent any solution state process as a state of matter as well in this kind of a context. So the 3 states of matter, solid, liquid, and gas, are each represented by the first letter of their state. And then an aqueous solution, or a solution dissolved in water, is represented by the AQ as a state of matter. Any special conditions like heating, which is represented by the Greek letter delta, or the presence of a catalyst or anything of that nature, are also represented in the reaction. And we have to be able to satisfy the law of conservation of matter in the chemical equation as well. So we write the equation starting with an arrow that will lead from the reactants to the products, and that's how we begin. Then we add in all of the other components surrounding this. So in order to write a chemical equation, we begin. So for instance, if we're going to take solid calcium carbonate, which will decompose by heating to form solid calcium oxide and gaseous carbon dioxide, we start off knowing what, or needing to know what the substances are involved in the reaction. So the reactant that we begin with is calcium carbonate, CaCO3. The products that are formed are calcium oxide and carbon dioxide. So we start off writing the reaction format. We begin with the reactant and then an arrow leading from reactant to product. Note that there is a plus sign in between both of the products, and this plus sign represents the fact that there are 2 products formed in the reaction and not simply 1. Our second step is to list the states of matter. Our initial problem tells us that we have solid calcium carbonate, solid calcium oxide, and gaseous carbon dioxide. So our calcium carbonate is a solid represented with an S, our calcium oxide is a solid represented with an S, and the carbon dioxide is a gas represented with a G. I will introduce this into the equation as a second step, and so now we have calcium carbonate as a solid reacting to form calcium oxide as a solid and carbon dioxide as a gas. The third step is to list any special conditions. Our reaction told us that we were heating this to facilitate the decomposition, so the use of heat is represented with the delta. We introduce this into the equation such that we have the delta over the arrow. Now conditions can be written on top of the arrow or below the arrow depending upon how many conditions we deal with. If there are more than we can fit on top, we'll start to put them below as well. The fourth step is to satisfy the law of conservation of matter. And to do this, we have to balance the equation. When we're balancing the equation, the process is to get the same number of atoms of each element, both in the product and reactant side of the equation. We use coefficients to balance this, and just like in mathematics, a coefficient is a number placed in front of the substance we're looking at. So in math, a coefficient would be like a 2 placed in front of an x. In chemistry, the coefficient is a number like a 2 placed in front of the chemical formula of the substance. And it tells us how many of that substance are involved in the reaction. Now there are 2 different numbers. Remember, there is a subscript which is written in the formula that only modifies an element. For example, for calcium carbonate, the blue 3 as a subscript modifies the oxygen, meaning there are 3 oxygen atoms per formula unit. The coefficient is written in front of the formula, and it modifies the entire formula. If I write a 2 in front of the calcium carbonate, the blue 2 modifies the entire compound. So it's multiplied by the subscripts of all of the elements in the compound. So I would have 2 calciums, 2 carbons, and 6 oxygens total if I had a coefficient of 2. Now, in order to balance the chemical equations, there are several steps that we have to go through. The first step is to count the number of moles of each atom on both sides of the equation. The second is to determine which elements are not balanced. The third is to balance the equation one element at a time. And then the fourth step is to double check our numbers to make sure that everything is balanced like we did in step 1. And we continue going through step 1 through 4 until we have a completely balanced chemical equation. Just go over and over and over again, changing things as they need to be changed. Now, one of the easiest methods to do this is to separate both sides and then list out all the elements. So for this, we'll start with the starting amount based upon the coefficients we begin with, which would normally be 1 if it's unbalanced. And then we will change the coefficients and change the number of atoms of each element. You should do this without erasing so you can keep track of the changes you make until the reaction is balanced. So for example, with our reaction we were just looking at, calcium carbonate going to calcium oxide and carbon dioxide. We start off by dividing the reaction in half. Along the arrow we have the calcium carbonate on the left and the calcium oxide and carbon dioxide on the right. We list out our elements, calcium, carbon, and oxygen. Our initial coefficients before we balance anything are 1, because we always have at least 1. And so taking into account a coefficient of 1 for each of these compounds, our number of elements comes out to be 1 for calcium on the left and 1 for calcium on the right. 1 for carbon on the left and 1 for carbon on the right. And 3 for oxygen on the left and 3 for oxygen on the right, because we add the 1 from the calcium oxide and the 2 from the carbon dioxide. Our numbers of atoms of each element are equal on both sides, which means nothing needs to be balanced. The equation is balanced as is. If the coefficient of the equation is 1, we will generally omit it from the final equation. And in any sort of balanced chemical equation, there must be at least one odd coefficient. So for this particular reaction, since all of the coefficients are 1, we would omit them all and have a general formula like this. As a more detailed example, if I have a reaction like this, we're starting off with 1 of octane, oxygen as reactants, producing carbon dioxide and water as products. If we look at this reaction, there's an even number of oxygens on the left because all the oxygens come from the O2 molecule, and no matter what coefficient I put in front of that, it will always be even. On the right-hand side, I have potential for odd numbers of oxygens. I have 1 oxygen only coming from the water, which means that if water's coefficient is odd, the number of waters will be odd. The number of oxygens overall will be odd, and so the number of oxygen on the right will be odd. If I can only have evens on the left and I have potential to get odd on the right, if there is an odd coefficient for the water, we can never have a balanced equation in that case. So in this case, we can never put a odd coefficient on the water in order for the equation to be balanced. If we write out our formula, set it up, put down our elements, there is carbon, hydrogen, and oxygen in this reaction. With starting coefficients of 1 for each of our compounds, we have 8 carbons on the left and 1 carbon on the right, 18 hydrogens on the left and 2 on the right, and 2 oxygens on the left and 3 on the right. Now, as we said, we cannot have a odd coefficient for water. So the first step that we can do is to double the existing coefficients to make that even. If I do this, everything becomes a 2, and I go from 8 to 16 for the carbon on the left, 1 to 2 on the right, 18 to 36 for the hydrogen on the left, 2 to 4 on the right, from 2 to 4 on the oxygen for the left, and 3 to 6 on the right. Now I go one by one balancing my elements. Because molecular oxygen on the left is by itself with no other elements involved, it's best to save that for last. Otherwise, we can pick any point. We can start with carbon, for instance. Carbon, there are 16 on the left and only 2 on the right. If I change the coefficient to 16 for my CO2, now I will have 16 carbons and a total of 34 oxygens, with 32 coming from CO2 and 2 of them coming from water. So my carbon is balanced left and right now. We move on to another element. Let's pick hydrogen, for instance. I can balance the hydrogen on the right by putting an 18 coefficient in front of the water. That is still even, so it's still applicable. 18 gives us a total of 36 hydrogens on the right, we had 36 on the left, so that is now balanced. The total number of oxygens between the 16 carbon dioxides and the 18 waters is 50. So now we only have 4 oxygen on the left and we have 50 on the right. So to balance the oxygen on the left, we have to change the coefficient to make 50. If I put a 25 in front of the oxygen, that will make a total of 50. Now I have 16 carbon, 36 hydrogen, 50 oxygen, and 50 oxygen. I have a balanced chemical equation.